Hello, everybody. Can you hear me?
Yes, we can. Hello.
Thank you. Okay, it's 12:30. We'll get started. I just want to make sure that, did anybody have any general, I'm not talking about specific questions about test 3. I did put a key up for that. And I also sent out a legend, I suppose, of the kinds of comments that I made in feedback. There were a bunch of abbreviations. So I put a legend out for those by email. If there's still people out there who aren't sure, you know, what the mistakes were, or if they want more clarification, please let me know. We'll talk about it. Okay, so let's look at on test 4. There is another naming quiz for this one as well. Although I don't think it's going to be as challenging as the last one. I think a lot of people usually find that this one is a whole lot easier. So alkenes and alkynes is what we're looking at. Alkenes, CC double bond, alkynes, CC triple bond. Alkenes end in ENE, and they need to have cis or trans, usually, not all the time, but usually cis and trans. And I'll let you know at those instances when cis and trans are not necessary to include. And then you've got the alkynes, which end in YNE, and those are not cis or trans because they're 180-degree bond angles. So there's no way to draw them cis or trans. So it's important when you're drawing alkenes to make sure that you include something that looks akin to a 120-degree bond angle. And in the case of an alkyne, make sure you draw it as a straight line, because it is incorrect to draw an alkyne like this. I see this all the time. I'm not real fond of this. But I do see that kind of thing, and I want you to know that that's incorrect. because the bond angles just don't match that. So when we're doing the naming of alkenes, the double bond will always take precedence in the name. We've already done a bit of naming of double bond compounds when we were looking at the naming of epoxides. So this one here, we've got 1, 2, 3. So that's going to be a heptene because there's 7 carbons, but it's trans 3 heptene because of the fact that the double bond is is off the 3rd carbon. And when you're trying to tell whether something is cis or trans, you look at the shape of the double bond. In the case of trans, you can see it looks like a zigzag. In the case of cis, it looks like a cup. So you can see the distinction I'm making here between what trans 3 heptene looks like and what cis 3 heptene looks like. Does anybody have any questions so far? Remember the ene part, ENE, is indicative of the double bond. The 3 tells of the position of the double bond in the chain from the end. And the double bond will always take precedence in the name, regardless of whatever else might happen to be in the name at the time. So an example here would be 88-difluoro-1-octene. You'll notice that it's not cis or trans. Now the reason for that is because if we were to draw this out, and I'm just going to show the hydrogens here on the end, not the whole thing, but just the hydrogens on the end. You'll notice that the fact that we've got the same thing attached to the end of the CC double bond indicates that we cannot determine cis or trans, just like we couldn't determine E or Z, if you remember back in test 2. And that's how we could know whether to say EZ or neither, if you remember. The same applies to cis and trans. So if you had something like this, you couldn't apply cis or trans to that either, regardless of what might be attached here or here. It doesn't matter. If these two groups are the same, there's no cis or trans in the name. Anybody have any questions?
This is only when it's on the end. That's the kind of.
No, it doesn't have to be on the end. I mean, Victoria, this would be an example where it's not on the end. The requirement is that as long as the two groups are different, will always be cis or trans.
Okay.
But generally speaking, we're really dealing only with 2 cases when practically you're dealing with names. And that's the cases where we have hydrogens next to each other or across from each other. You won't have to worry about E or Z.
Thank you.
Sorry, that's cis. Sorry. Okay, so that's trans, that's cis. All right, anybody have any questions? So again, with that same name, it's not cis or trans, that's the first thing. The other thing is that because the double bond is taking precedence in the name, as far as the numbering goes, we number from this end. We number from the end of the double bond. Even though it looks as though it creates a numbering set that is greater than what it should be. But that's only because the double bond is taking precedence in the name. In the naming of alkenes that are cyclic, we number through the double bond to whatever happens to be connected to the ring, again, trying to get that lowest possible numbering. Does anybody have any questions? So in this instance, it wouldn't be prudent. Let me draw this diagram here. You might think, oh, I'll just number this way. But you've got to number through the double bond. So the 1 here is at the beginning of the double bond, and then you've got the 2, and that's the way I've got it numbered here. So you've got to number through the double bond. It takes precedence in the numbering. So the number 1 would always be at the double bond in the cyclic case, but it has to number. You have to number through the double bond, not at the other end of it. So that's what I'm trying to point out there. So you can see in this instance, the numbering here for this one is 1, 2, and then you've got 3, 3-dibromo, and then 6 on the fluoro. So again, the numbering has to be through the double bond. So I guess a good way to remember it is to realize that the situation is always going to be like this. It's always going to be 1, 2, always. But then or it could be 2, 1, I suppose, like this. But then whether it's 1, 2 or 2, 1 is going to depend entirely on what's going to result in the smallest numbering for the rest of the groups that are attached to the ring. And that's what we're achieving here. Does anybody have any questions about the naming of alkenes or alkynes at this point? So again, you'll find this in the test 4 folder. It's a quiz. It's a practice quiz for the naming. And then you've got the credit quiz once you get 80% on the practice quiz. As I said, I truly believe that this is going to be easier for you than the previous one. So you shouldn't fear it. And again, I would recommend getting it done straight away. Get it done tonight. You don't have to worry about it after that. A lot of people won't heed my advice. They'll just decide to leave it till the last minute. But then they'll have to make that horrible choice between studying and doing the naming quiz, which is part of their grade. And, I don't really want that to happen. All right, does anybody have any questions? Okay. So I'm going to go through reactions here. We're going to start with some syntheses of alkenes, or how we make alkenes. And we've actually already dealt with a few methods here for making alkenes. This first one here is the situation where we have a symmetric alcohol. Now, by symmetric, what I mean is that if you draw the alcohol here, there's a plane of symmetry through the C that has the OH. So what that means is that we would end up with, as a product of dehydration, that's the addition of H plus here, and you can see that the double bond could rest on either side, but that it would result in the same compound. So these are the same. And that's only because, and we know this because the initial compound, one with the OH on it, did happen to be symmetric. The corollary of that, of course, is that if the alcohol is not symmetric, there'll be more than one product. If it's completely asymmetric, then there'll be as many products as possible. Now you can see the mechanism here for this. I've expressed this as an E2 mechanism because, as we discussed in test 3, in these kinds of situations when we are using the dehydration, E2 will always be an effective mechanism. E1 is one that we can't count on all the time for certain OHs in certain positions, especially the primary position. So the first step is always going to be addition of the H+. Now, when we're talking about H+, there's no water involved here. It's usually concentrated sulfuric acid, which has an incredibly small water content. And it has so little water, in fact, that it effectively doesn't really have any because all the water is protonated with H+. For any water that happens to be in the concentrated solution. And the pattern is always what we had talked about, like in test 3. Now, for a lot of you, you would have seen my corrections on test 3, and I had a lot of abbreviations there, like arrow not from bond or arrow not to bond or arrow not to atom, that kind of thing, or an arrow not from atom, it's even as well. So all of those, you've got to be very careful about where the arrows are coming from and where they're going to. This one's coming from the bond and going into the bond. I'm going to redraw that, make it a bit bigger. Let's do that. Okay, so take special note of that. So you see where the electron's coming from the bond, not the atom. And they're going into the bond because we are making a double bond here. And then this arrow is coming from the bond and going on to the atom. And then we have H plus as a result of the breaking of that bond, and H2O as a result of breaking the other bond. Does anybody have any questions?
I do, because I got this wrong on the test, I think. So you said the arrow from the bond to the atom, that's the water leaving, right?
Arrow from the bond, yes, that's right, yes.
Okay.
That would be correct. Do you have any other questions about that, Deanna? I mean, to help clear that up?
No, I just remember that was one of my abbreviations that I got on my test. And so I was just trying to make sure that's what you were talking about.
Well, make sure you understand it in the context of the question you got wrong as well. Exactly what I mean.
Okay.
Okay. And if you don't, you'll let me know.
Okay.
All right. Because I think it's really important. Sometimes people think I'm a bit too picky about what I want for the arrows.
I think I know exactly what I did, but it was just me moving fast. And so the arrow wasn't on the atom. It was just out towards nothing.
Yeah. So, sorry, Deanna, I wasn't trying to say anything about you specifically.
No, it's okay.
Yeah, I'm just saying generally speaking, this is what I find, that there is an exactness to it. The arrows are telling a story, and we want to be telling true stories. All right. Anybody got any questions? So as you can see, I did show you the mechanism for the symmetric one here. The mechanism for an asymmetric one is identical, except that we're going to be able to have the possibility of removing a hydrogen from either side. We saw something like this when we were looking at question 2 in test 3 as well. Does anybody have any other questions about dehydration? I think the message there is drink more water. Feeling dehydrated? Drink more water. We've got another way that we can create alkenes. This is something we've seen as well. We saw this back in test 2. And that's the elimination process. And if you remember, we can achieve elimination here by using OH minus and heat. That's a strong base and heat. This example is for a symmetric one, but the asymmetric rules still apply that we talked about earlier. So you've got Br here. And it's pretty similar to the one we just did. This is still an E2 mechanism. And you can see the arrow here goes from the OH minus to the H. Then the arrow comes from the bond and goes to the bond. And from the bond to the atom, like that. See, it's beautiful. It tells that story I like to see. And we end up getting Br minus as a result of that. And H2O as well. Does anybody have any questions? Okay. Now, we briefly touched on reactions similar to this next one, hydrohalogenation, except what it was hydration that we looked at. But I was careful back in test 3 not to deal with any alkenes that were not symmetric. And I didn't want to deal with that because we have a complication that arises when an alkene is not symmetric. And that complication is due to what we call the Machovnikov Rule. So let's go through that in this context, and then we can go back to hydration in a minute and show what happens if we're using an asymmetric alkene in that instance. So if we've got an alkene and we're adding HCl to it, you'll notice that this alkene is more substituted on one side than it is the other. And that's really the key to what I'm talking about here. So when we add H+ to the double bond, there is the possibility that we could have the H+ join in this way, where the plus ends up on the left C and the H ends up on the right C, which is the correct method. But the other possibility is this one. And that would be putting the positive charge on this carbon here. That would be the incorrect method. So what's the distinction that's made between these? Well, it all comes down to the kind of the kind of carbocation we're dealing with. So a tertiary C+, one where there's 3 carbons connected to the C, is going to be more stable than a secondary C+, which is more stable, again, than a primary C+. And you can see this distinction that I'm making here between these. The kind of C+ we're dealing with here, it happens to be tertiary. And the C+ we're looking at here happens to be secondary. Now, I don't really want to go into this again about why tertiary is more stable than secondary is more stable than primary. I'd like you to go back to test 2 to look at that. When we were talking about SN1, SN2 reactions, that's when we talked about the distinction between the stability between tertiary, secondary, and primary C+. But the bottom line here is that when there's a choice, it'll always go on the carbon that will result in greater substitution. In other words, the tertiary will always take precedence over the secondary possibility or the primary possibility. Now, once we've got the Cl- located there, once we've got the C+ located there, then we can add the Cl-, and the Cl-, of course, will go to the same location. The Machovnikov Rule basically states that during this kind of reaction, the halogen will always end up on the more substituted of the 2 carbons. You'll notice here I'm not even going to draw in that hydrogen. But look where the Cl ends up. So you look at the double bond and you ask yourself, well, which double bond has more Cs on it? And the one with the more Cs on it, that's the side it will go on. It's really that simple. Does anybody have any questions as to what's going on there?
I don't have a question, but I'd like to point out something funny, that Markovnikov's rule is also Russian.
Yes.
And that means a carrot. Just
Oh,
like
that means a carrot.
Yes.
I thought Zaitsev meant carrot.
Zaitsev rule means rabbit. So
rabbit.
How funny is it's all about carrots.
Carrots and rabbits. Oh, all right. Okay. Well, thank you for clearing that up, Victoria.
My pleasure.
Rabbits and carrots. Wow.
I don't know what kind of secret societies they had there, that they all had a similar last name meaning, but it's actually funny.
Yeah. Oh, reminds me of Monty Python and the Holy Grail, but we won't get into that. Okay. So Machovnikov's rule, when HX is attached to the double bond, the X will attach to the more substituted C of the bond. In other words, the X group of the HX will go on the C that has more Cs on it. So an example would be, when you're looking at this slide here, you can see the C double bond. The top C is the one that has the most Cs connected to it. Look where the X ends up on that C. In the example below it, you can see the double bond here. There's no carbons connected to the right end, but there is one carbon connected to the left end, which means that's where the X connects, on the left end of where the double bond was. Does anybody have any questions? So the reasoning, of course, has to do with where the plus forms during the mechanism. We notice a similar pattern with hydration. And as I had said earlier, with B here, this is something we've already seen. We saw this in test 3, but I was very careful not to deal with these kinds of alkenes, the ones that were asymmetric. When an alkene is not symmetric, then the OH does end up in a specific location. Again, the OH will end up on the more substituted of the 2 carbons that make up the double bond. So again, we arrange it so that the H goes on the less substituted carbon. The plus ends up on the greater substituted carbon, more carbons around it. The O attacks the plus. And you can see where the arrow is coming from. It's coming from the O and it's going to the C+. And that's forming a bond. And then we lose the H+, and lo and behold, it's like I said, the OH has ended up on the C that had more Cs connected to it. Does anybody have any questions? Now C, hydroxymercuration, is a similar reaction to B. It does the same thing, follows Machovnikov's rule, but it usually has a higher yield. But we're actually, you won't be asked, I can tell you this straight away, you're not going to be asked about hydroxymercuration. I'm just including it because, well, it's in the curriculum document, but we're not going to be having any reactions on the test that relate to that. Does anybody have any questions so far? So we know with hydration that the OH does end up on the C that has the most Cs connected to it. But wouldn't it be nice if we had a reaction where the OH would end up on the other C? And we actually do, and it's called hydroboration. We call this anti-Machovnikov addition because the OH ends up on the least substituted of the 2 carbons. It's a misnomer really because there's nothing anti about it. It's just a manipulation because we're using a different kind of reagent to make this reaction happen. So again, anti-Machovnikov addition. All right, so we're using the reagent here, diborane, which is a B2H6. I'll show you what that looks like. So you can see by its nature, the borane is actually electron deficient. It has a vacant space here that would like to be able to fill up its octet. So what it will do is often it will form a, no, well, not often it will form a dimer. A dimer is the joining of two single parts that can be easily split apart. So this will easily split into two BH3s, which has this vacant space here. And B, by its nature, is going to be less electronegative than hydrogen. So the nature of the BH bond itself is like this. Actually, B is delta plus and H is delta minus. But when I'm looking at BH3, I kind of think of it like this. I kind of think of it like BH2 plus and H minus together, like that. So what's happening here in this reaction is that the BH2 plus is kind of acting like the H plus did in the previous example, which is why we end up being able to manipulate this in such a way that it appears that we are creating an anti-Machovnikov situation, something that's breaking the rules, but we really aren't. We're following the same rules. So instead of H plus, it's really BH2 plus that we're using. Okay, so BH2 plus. And it takes the same arrangement as we did before, where the plus ends up on the more substituted of the two carbons. And then the H minus can come in and attack that carbon's got a plus on it. And you can see we end up getting this BH2 here. And it's ending up on the less substituted carbon. Then we can treat this with H2O2 and OH minus, which is not something I really want you to worry about too much as to exactly how that's working. Which leads us to that BH2 being replaced with an OH. And so it appears that the OH ends up on the less substituted of the two carbons, which it does. I mean, it's not how it appears about it, it does. But it's the opposite to what happened when we dealt with hydration in the previous example. Now, I mean, that's my explanation for why the mechanism goes the way it does. But in reality, it doesn't actually go that way. It goes more like this. You can see it up here. I'll do the real, what it really does up here. But I guess what I'm showing you is an explanation for why it takes the route that it does. It's really actually a concerted process, happens in one step. And we end up getting, well, actually, you shouldn't say that. The arrow goes down here. We end up getting this in one step instead of two. But the reason it goes in that direction with the H on the left and the BH2 on the right is because of the formation of that positive charge in the more stable place, the tertiary place. Does anybody have any questions? All right, allow me to summarize that and I'll show you what I mean. So let's say we've got this situation and we're being asked, well, what happens when we add H3O plus or H plus and H2O. Well, what we expect to have happen there is the OH will end up on the more substituted of 2 carbons. There we go, like that. But if we treat this same alkene with the first step, B2H6, or you might see BH3 here as well. And the second step, H2O2 and OH minus, then what we're going to see there is the OH on the end, like that. So you can see the difference between the two. It's fairly simple. One goes on the more substituted C and the other one goes on the less substituted C of the double bond. Does anybody have any questions? And allow me to remind you all that there will be no class on Wednesday. Wednesday is Veterans Day. There are no classes at all on Wednesday. No lab either, right? But I think most people in the lab know that. Keisha, do you want to say something? Okay.
Sorry, I don't know. I got unmuted. I'm sorry.
No, you're good. You're good. Okay. All right, the next one we're dealing with is halogenation. If you're doing the lab, or at least my lab section, then you know a little bit about this because we've been dealing with the stereochemical consequences of bromination of the double bond. But we're going to really mainly focus on the bromination of cyclic structures like the one you see here. And you're getting the compound here with this specific stereochemistry. And what happens is that the first thing that happens is that we end up getting this now, I suppose I'll do it from, I suppose we could do it either way, really. I'll do it from here. And what we end up with is this triangular brominium ion. And you'll notice it has a very specific stereochemistry. I mean, it can be either up or down. But if you look at the side view that I have here, you'll notice I've purposely drawn this Br plus so it sticks up from the ring. Now, this is important because what it means is a Br minus will come in to attack, but it will attack from underneath, from the underside of the ring, and produce something that has a very specific trans stereochemistry. So the result is a Br that sticks up like that, and a Br that sticks down like that, and all because it had to come in from underneath. Now, I want to give you a little bit of a reminder here as to bond angles and the nature of the bond. So in the case of any alkene, it's flat or planar. In this instance, this is not flat because it's not a double bond. It's an sp3 hybridized carbon, or essentially is. And there are 2 hydrogens connected here. I haven't shown them. But if I did, those hydrogens would be drawn pointing downwards. But I don't really want to talk about those hydrogens too much. Because, you know, we don't really need to draw them in. We're only interested in what's going on with the bromine. All right, does anybody have any questions about this one?
So in the example, there are two products.
Yes, because they're mirror images, they're enantiomers, and they're non-superimposable mirror images.
Is that, are you getting the two products because you went through it this way and got the one product with the one bromine underneath? No, I'm trying to look.
I get it. I get it. I get what you're saying. Now,
Okay.
effectively, Rebecca, I'll show you. It's really a 50-50 shot. Now, you know, the BR is definitely going to come up from underneath. There's no question about that. But there is an open question as to which carbon it attacks, right?
Okay.
So you can see here that if it attacks on the top C, we'll get actually the opposite enantiomer. It's not the same thing. It might look the same, but it's actually different. And it happens to be non-superimposable. With the one I drew up here. I can try and flip that over, but it's not going to match up with the one that I've got up here. So we end up getting two products essentially. Now on the test, I'm not going to be that mean about it. As long as you draw one of the enantiomers, I'll be happy with Larry.
Okay.
It warms my heart to see both, but my heart doesn't need to be that warm.
If you're grading our tests, it probably does. But on the PowerPoint, it looks like it's showing your first, I would guess I would call it more cis structure as one of the products. Am I not seeing that correctly?
Well, it's
Where it sounds to me like you're saying the trans bromine structures are the actual two products, and as long as it's one of those, it's correct.
Yes, but you don't get any cis.
But is that a cis product at the top, where your cursor is? No, it's dashed at the top.
It's dashed at the top.
Okay, all right, that's just the resolution of my screen. Thank you.
Yeah. Oh, well, if you zoom in on it, I mean, I'm not saying you can zoom in on the screen. If you zoom in on the PowerPoint notes, let's see, maybe I can do it. It'll become a little bit more clear. Let's start over. There you go. See? Is that better?
Yes, yes. I thought the second one had two wedges.
Right. That would not be good. All right. I'm actually going to skip F, right? I promise I won't ask a question about on the test, right? I'm skipping F. Skipping up. Skipping up. Let's go to G. Did you notice that? I skipped F. It's gone. I promise. Nothing about F on the test. All right. I'm going to show you two reactions here that result in what we call diols. Now, diols are compounds that have two alcohol groups, di for two, ol for alcohol, so two alcohol groups. As you can see here in both of these slides, I've got them juxtaposed. Depending upon the kind of reaction you're doing, or the reagent you use, you can end up with cis diol or you can end up with a trans diol. So to get a cis diol, what we use is this wonderful compound called osmium tetroxide. Now, osmium is an incredibly, well, in elemental form, it's an incredibly dense metal. I think it's probably the densest metal. I think it's like 21 grams per mil or something like that. It's about double as dense as lead, actually. But the compound OSO4 is actually a very nasty compound. If it gets in your eye, you can say goodbye to your eyesight and say hello to cataracts and eye cancer. It's a very nasty kind of thing. In fact, I'm not even sure I can look at it now, but I'll survive, I think. So the idea is that if we use this OSO4, then we end up getting a cis diol at the end here. The second step involves mannitol or NaHSO4. Now, these are used as, in this instance, as reducing agents. Mannitol, some people might even, if you have anything to do with nursing or drugs or anything like that, mannitol looks like this. 1, 2, 3, 4, 5, 6. One thing you'll notice about it has a lot of OH groups on it. And it's a good reducing agent because it can be oxidized in many instances to a C double bond O. I'm not going to do it for all of them, but you know, you can get that.
I assume this compound might be acidic.
No, it's not acidic actually. It's has anybody ever heard of it before?
Yes, you give mannitol to drop the pressure.
Yeah, okay, yeah. There's another, it's also a diuretic.
True.
And the reason for that is because of you can see, look at all these OHs here. So it's very water soluble. So it will pull water out of anything. So it's very, very soluble in water with all these OHs.
Which is
not acidic though. Go on. Sorry.
Oh, I'm sorry. I'm sorry. My computer delayed. I was saying that you drop the pressure by diuresing as well. Like you said.
Oh, yes. Yeah, there you go. Yes. So it's diuresis, right? That's what I'm describing.
Yep.
Yeah. So this acts a little bit differently though. What it's doing here is it's taking the compound that we get from this OSO4, and then we're adding hydrogens to the OHs, and that's all the mannitol is really doing. It's a reduction process. But the first step is really the most important one because it defines or ends up defining the stereochemistry of the product, which is really the key here. Remember, we're trying to explain why this is forming a cis double bond. I'm going to draw this a bit bigger. I don't like it. Hang on. So this is called an electrocyclic reaction because all of these arrows are occurring at the same time. I'm going to draw this in 3D, what this looks like once it joins onto the osmium and the oxygens here. Because they all sort of broke and formed all at the same time, you can see that we end up with a very specific cis stereochemistry. And then the mannitol comes in and breaks that off and puts hydrogens on the oxygens. So we end up with a cis product at the end. Does anybody have any questions? Okay, and obviously I don't need you to know what's going on with the reduction part. It's really the first part that I want you to focus on. So that's a good way to make cis diols. We also have a method of making trans diols as well. The method involves using a reaction that we dealt with back in test 3. And that was the reaction that allowed us to form an epoxide, and then the OH minus comes in from underneath that, and then we get the cis diol. So this is very much like the bromination process we just looked at not very long ago. Because when we form the epoxide, and you can see it here on the slide, the O points up above the ring, which means the OH minus comes in from underneath, and we end up getting that very specific trans stereochemistry. In the final step, the O minus takes a hydrogen off water, and we end up getting the trans diol as a product. So again, we're seeing this same situation where we have two different reagents that produce two different kinds of products depending upon what we want. If we want a cis diol, then we would use the osmium tetroxide, the OSO4. And if we wanted a trans diol, then we would use the MCPBA and the OH minus in the second step to produce that. Does anybody have any questions? Okay. I'm going to skip over ozonolysis for now. It has relevance to our roadmap problem, but I don't really want to talk about that until we get into the roadmap. And the roadmap is going to use a couple of other reactions we're going to see as well. But the ozonolysis is going to be very important for the roadmap. So please bear with me while I skip over this, and we will come back to it, I promise. Okay, the next one is called the Simmons-Smith reaction. And Simmons-Smith reaction allows us to take a CC double bond and turn it into a cyclopropane type compound. It looks familiar to me. I mean, I think it looks a lot like epoxidation. The difference being that instead of putting an O there, we put a CH2 there instead. And you'll notice that it has something in common with the MCPBA reaction in that if you have a cis double bond, you end up with a cis ring. If you have a trans double bond, you end up with a trans ring. But the result is always a 3-membered ring, a cyclopropane ring. The mechanism is as follows here. The CH2I2 and the zinc CnCu here, it's called the zinc copper couple. And it has to do with it's kind of like a battery in a way. And it runs an electric current through CH2I2 and turns it into this creature, which is CH2, which is a wonderful creature called a carbene. Very, very unstable, but unstable in that it produces a very electron deficient kind of species. And that electron deficient species reacts with the double bond here, and we end up getting a cyclopropane ring as a product. So that would be the mechanism for that one there. But again, cis and trans. So cis double bond, cis ring, trans double bond, trans ring. Does anybody have any questions about the Simmons-Smith reaction? Okay. The next reaction is hydrogenation. And hydrogenation is the process by which hydrogen gets added to a CC double bond. And if you look at the diagram here, I'm going to go ahead and enlarge it. It doesn't have a great deal of relevance when the double bond is not in a ring. But when it's in a ring, we have the ability to actually see the stereochemistry of the way that the hydrogen adds to the ring. What we're using here is hydrogen gas and palladium metal. And the palladium here is a catalyst. We definitely need the palladium. If we didn't have the palladium, this wouldn't work. So what happens is the hydrogen actually bonds to the palladium in the manner I'm showing here in the diagram. And then I kind of like to imagine the ring here as being like a spaceship, you know, like an alien craft of some description that kind of comes down and attaches to the two hydrogens here. See, my fingers here are the hydrogens, and you've got the ring coming down on top of that, which explains the stereochemistry of the product that we get. And you can see the two hydrogens have attached underneath and pushed the two methyl groups upwards, which is why we end up with the product that we see here. Did I have to show the hydrogens? No, no. If I just showed the stereochemistry of the methyl groups, that would have been fine as well. But the point is that it's something that we know adds to the ring with predictable stereochemistry. Does anybody have any questions? I know it's a lot. It's a lot to go through. It's the same kind of situation as we saw with test 3, and I will go over those reactions, but there's only certain ones that I'm going to say that you really need to know the mechanisms of. Actually, in fact, there's only one mechanism question in the entire test that it's actually for credit. And I'll get to that in a bit. The rest of the mechanism questions are all for really extra credit. So there's only one that's for credit, and it's only one reaction. I'll tell you exactly which one it is. Isn't that wonderful? I think it is. All right. So those are all the alkene reactions that we're going to go through. And there's many fewer reactions here on the alkynes. And alkynes are made, it's kind of like a double elimination, really. If you remember, I had a reaction way back here. I'll show you now. Remember, this has got two bromines on it side by side, right? There's this one here. If you've got one bromine, you get one double bond, right? So one bromine, one double bond. The reaction we're looking at here has two bromines next to each other. And it's almost like it's kind of two double bonds, but they end up making a triple. As you can see, we end up doing the same thing twice and end up getting a triple bond as a product. Now, we've got to be a little bit careful about the way we do this mechanism, but it's the same kind of mechanism that I showed you on the previous example. So it's a side-by-side bromide, also called a bisanol dibromide. The elimination reaction occurs twice, and then you end up with this alkyne, which has this linear kind of geometry I talked about earlier. Does anybody have any questions? Again, you know, I'm telling you, there's only one mechanism you need to know. We haven't even gotten to it yet. Only one mechanism you need to know. You haven't even gotten to it. Once we get to it, I'll tell you. I'll make it very clear. And when you look back through all the old tests, you'll notice, I think, a real similarity between the mechanism questions. All right, so that's synthesis of alkynes. Does anybody have any questions? anything optional, I'm going to skip over the optional part here, in the interest of time. All right, reactions of alkynes. You see, we're almost going to get through all the reactions today, almost all of them. Not quite all of them, but almost all of them. Now, we already went through hydrogenation of alkenes, and that was the one that looked like a spaceship. That's this one here. Now, if you're doing alkynes, a similar thing happens, but it's what happens is the first thing we get is an alkene, and then the alkene reacts, and we end up with an alkane as a product. So the hydrogen adds twice to the triple bond. This is actually really interesting, this first step here, because we end up with a very interesting product that's a cis alkene. And if we can find a way, and I'm going to show you there is a way, that we can add hydrogen to this so that the reaction stops here and it doesn't go any further than that. Well, we end up having to poisoning the catalyst in order to make that happen. But if the catalyst isn't poisoned, if we just use straight hydrogen palladium, then we don't get to see this compound. We don't get to see this alkene form. What will happen is it will react with the hydrogen twice, and we'll end up with an alkane as a product and not an alkene. Does anybody have any questions about that one? Yeah, I don't want you to get too caught up on the mechanisms for these. If I'm not going through the mechanisms, it's because I believe that they're not that important, all right? Because, well, you won't be graded on it. I'm not saying the mechanisms are useless, but, you know, I'm just saying. So applying what I was just talking about here, if we had, you look at the difference. This one is just straight H2 and PD, but if we use CaSO4 and quinoline, also you might see BaSO4 as well in quinoline. What that will do is that CaSO4 and quinoline will attach to the surface of the palladium. It poisons the palladium, poisons the catalyst, and it slows down this process here where the hydrogens are added to the palladium. So when that happens, yeah, I mean, it still happens, but it happens a lot more slowly. And we're actually able to isolate this alkene, and it won't go any further than that. Yeah, it's called, I have a name for it if you want to look it up. Lindlar catalyst. So it's used to slow down this hydrogenation process so that we don't end up with the alkane like we did in the previous one. So it stops at the, and it's cool, it's a cis alkene. A cis alkene is a product. That's with the poison catalyst. Anybody have any questions? Okay. So we've got a way here to produce a cis alkene, but what about a trans alkene? Well, if we use this specific set of reagents, then we can end up with a trans alkene. It's sodium, ammonia, and FeCl3. The difference is, you can see in the hydrogenation with the poison catalyst, we end up with a cis alkene. If we use this particular set of reagents, we end up with a trans alkene. And again, this mechanism is not one you have to know. It's not one you have to know. But because of the way that the mechanism goes, we do end up with this trans configuration at the end. And again, I'm not going to go into that. If you want to watch my video, you can. And the mechanism itself, again, it's not going to be for credit. You might see it as part of question 1, but you won't see it as a mechanism question, I can guarantee you. All I want you to be aware of at this point is that there's a way to create a cis alkene and a way to create a trans alkene from an alkyne, a triple bond compound. Does anybody have any questions? Well, hydration, this is actually the only mechanism you'll have to know for the test. the only one that you'll actually have to do a mechanism for. And you know, it's not even really that bad a mechanism. So I'm going to go through this one because you'll actually be asked questions about it. So this first one is the hydration, a terminal alkyne. Now, by terminal, what I mean is that it ends in a hydrogen. There's a hydrogen on the end of it. That makes the alkyne effectively asymmetric, if you will. So it's going to follow similar rules to what we talked about at the beginning of the class. The mercury here is necessary, but it doesn't really play into the mechanism. I believe what it does is it kind of adds to the triple bond and makes the triple bond more reactive. But you'll notice that it's never really mentioned as part of the mechanism. It's not really, it's necessary for the reaction to go, but it's not really going to be important as far as how the reaction's proceeding. Okay, so let's have a look. So what happens is we add H plus to this triple bond, and it will do something similar to what H plus does when it adds to a double bond. Now the plus, of course, will end up on the more substituted carbon, just like it did previously. So I'll put that H here. We'll add the H here as well, I suppose. So one of these is the H from the H plus, okay? That's that one there. And then water comes in and attacks that C plus. So it's very much like the hydration process we looked at earlier. Then we lose the H plus. And we end up with this compound that is called an enol. En because of the double bond, ol because of the alcohol. But really, an enol is actually in equilibrium with a ketone. Enols are very unstable, so they'll break down into ketones. And since we've got the acid in there anyway, you can see how that can happen. So the ketone is a C double bond O like that. And that would be the complete mechanism for hydration. So you're going to get something very similar to this on the test. I'll show you pretty much what you're going to get in a minute. Does anybody have any questions about that mechanism? Okay, so that's for terminal alkynes. This would be a symmetric alkyne. It's exactly the same mechanism. So you'll notice, sorry, go on, Rebecca.
No, it's Julie.
Oh, sorry, Julie.
I have a question.
Yeah.
So it was an enol, and then all of a sudden it became a ketone.
Yes.
So it lost an H.
It didn't lose an H. The H moved effectively.
It just hopped over to the end.
Yeah. Yeah. So really, the net effect here is this H, the one I circled, Julie.
Yeah.
And ends up on this hydrogen. Sorry, it ends up on this carbon on the end.
Okay.
And you end up with a double bond here. The reason it does that is because the ketone form is much more stable than the enol form.
Okay.
Okay. And if it's a symmetric alkyne, you'll notice it doesn't matter which side the C double bond O goes on. And if it's an asymmetric alkyne, Look, I'm going to tell you. I'm going to tell you straight. This is what you're going to see on the. This is what you're going to see on the test. This thing you're looking at right here. Okay, that's what you're going to see. So it's the same mechanism, and because it doesn't matter which side the plus goes on, because they're both the same stability, you end up with these two different products, two different ketone products. So this is what you're going to see on the test. I'll say it again. This is the mechanism question you'll see on the test. The only mechanism question you'll see on the test that's for credit. Can you believe it? Yeah. Does anybody have any questions about it? I mean, look, it's the same mechanism as I just went through. It's just applied twice, once to each side, because again, during this first H plus addition step, it could go either way. The H could end up here and the plus next to it, or the H ends up here and the plus next to it. That results in the two different sets of products. That's all I really want you to understand. Does anybody have any questions? Nobody has any questions. I can't believe anybody has any questions. All right. I know you've seen a lot of reactions today, but all right, but that's pretty much it. That's most of the reactions. I think it's all the reactions actually. All right, let's take a look at the kinds of resources that you have here to look at. Remember, there's no class on Wednesday. Next Monday, we're going to be starting on some spectroscopy. Well, actually, no, we'll do a little bit of stuff to do with the roadmaps first, and then we'll get into spectroscopy. So, you know, I still want to go over osmosis. I haven't done that yet. I can't do it in 5 minutes. I won't do it in 5 minutes. All right, let's take a look at problems test. Okay, I've got a similar setup. I've got the reaction summaries that have the stars on them. They're really more suggestions. They're ones I think you should know. You don't have to know them, but you should know them. I've got a naming exercise here as well with the answers. And then I've got the same setup as I had previously in test 3. So starting on page, what page is that? Page 12. You'll have all of these different examples that you can do and then compare them against another file, just like we did for test 3. Same kind of deal. That's so you can learn the mechanisms. You'll notice for some of these, I have a star on one part of it. If you want the bonus credit, then you'll do the ones with just the star here. See, I don't require a mechanism for part 2 on this one, for example. Likewise here on the cis diol formation. That one is only the top one that's starred. And on the trans diol formation, it's the bottom one that's starred. So that's all the reactions there and the mechanisms. So you've got plenty of stuff to work on. And then after that, there's all of these here. There's what, 70, 80, 89 of those to look at. So you can do the mechanisms for them, a good practice just to see if you can figure out what the products are. And of course, the answers for those are here as well. And the mechanisms are in that same mechanism file for all of those, all 89 of them. So, you know, you've got plenty to look at.
Do the stars indicate we can do mechanisms for those?
I'd recommend it. I think it's good to know the mechanisms because the mechanism serves a purpose. It'll help you to get the product. That's just my opinion.
Is there any difference between the big stars and the small stars?
No,
Okay.
no. Big stars are usually hotter. I'm just kidding. I'm just joking. All right. No. No difference. Does anybody have any other questions so far? Okay, so we'll continue on Monday. I'll do the ozonolysis. That'll be the end of that, and then I can start on the spectroscopy, and we'll be on track. All right. Remember, no school Wednesday. Right, no school Wednesday. Okay.
Compared to the totality of the last test, how is this test looking?
Difficulty wise.
Yeah, difficulty, technicality. I mean, you know, you had said that third test was going to be.
I'd
one
say
of
it
the
was the
best.
worst. I think the third test is the worst. I think this one's a little better. In my opinion, people might not agree.
Well, understanding the mechanisms made it easier. I mean, I just noticed when I was going through the lectures, it seemed familiar, whereas last test it did not.
Oh no, well, you see, that's the thing. There's a lot of similarity between test 3 and test 4, especially
Okay.
the mechanisms there.
Okay.
And that's why I think it's foundation. That's why I find test 3 is foundational for test 4. People who do well on test 3 usually do well on test 4. People who didn't do so well on test 3, mixed. I'll just say that. Yeah.
Have a chance at redemption.
It's always redemption, Rebecca. There's always redemption. All right. Any other questions? Okay. Well then, I'll see you all anon.
Bye-bye.
Bye. Thanks for coming.
Dr. Musgrave?
Courtney.
Yes, I have a question pertaining to lab. So I was calculating my grade, and with one of my lowest grades that's dropped is a 95.
Oh,
Is
nothing's dropped yet, Courtney. Remember that last workday worksheet
Okay.
is part of your grade.
That's what I was saying. Like,
That's the one that's dropped now.
Really, because in the grade book it shows that.
No, just ignore. Well, ignore that.
Okay, I was calculating my points, and it looks like I have a 93 with getting a 0 on both the last day and the NMR.
Oh well, then
Yeah.
aren't you lucky?
Yeah, that's what I wanted to confirm it though. Like
Well, no. If your current points, if you look at your current points and it's more than what's required for an A, then you have an A.
See, that's the issue though, is that the points that are in the grade book is a B, but that's with one of the A's dropped.
Oh, okay. Hang on. Then
because it shows one of like, I think it was like aspirin is dropped, and I got an A on it.
Okay, I'll have to look at it, Courtney, but I don't know. I'll yeah. Look, wait a second. We'll see if there's anything else here, right? Then I'll look at it. All right.
Okay, thank you so much.
So don't go anywhere for a second.
Okay.
I'm going to stop recording.